Okay, I have reconstructed our diagram from yesterday. What I want to do is begin by showing that this orientation of future is in fact continuous and smooth. Just visually looking at it, it is continuous. But what might seem odd, and something that requires clarification perhaps, I'll do it with n, the same thing applies to L. Fact of the matter is, you don't need both vectors to pick a light cone, you just need one vector. So n is sufficient, but if you look at this as we go across the horizon here, there's a minus n and n minus n. So it just appears odd, but it's in fact a smooth assignment. Notice this is an r plus horizon. This is also r plus horizon. The reason these two appear is this is r star equals r plus, while this one is the r bar equals r plus horizon. And so at the moment, the horizons have been included by going through various patches. We don't know about the center point here. By that I mean, of course, v plus equals 0 and u plus equals 0. We'll fill that hole in, but meaningfully by looking at the geodesics along the horizon. Okay, so my first goal is to show continuity of orientation of future, or rather that n is this yellow vector field is continuous across the horizon. That'll do it, because it is certainly continuous across this horizon. Okay, so I should perhaps mention that while these videos are posted elsewhere or uploaded elsewhere, perhaps on YouTube, we'll host all the links to the videos on a center site, and there I'll have my notes for these lectures. That way you'll have all the equations handy, and more importantly, correct, hopefully. And if I've said something erroneous while lecturing, just not being very careful or not paying attention to detail, once again, hopefully, it is a corrected version in the notes. So I haven't defined f, but I will. One bar prime and 2 bar prime, u plus is equal to minus f, where this f is a very temporary thing. It's just to show this result. It doesn't have any long-standing meaning. Yeah, we had shown this, I just called it f, that's all. Kappa plus 2r minus t. Nope, I think this is t bar. Yeah, I think it's t bar. Okay, and I would also like to note that minus of a prime a over r plus squared plus a squared t prime is equal to a over r plus squared plus a squared r minus r plus r minus r minus. The prime here is derivative with respect to r, or even r bar. Okay, I have given you expressions for a and t. You just take the derivative. This is easy to verify. Okay, so I have a small piece of real estate here. So n is given by, okay? Now along n, v equals a constant because v is a function of t bar and t bar is a constant. So n goes this way. So n can have at most three components: the u component, the theta component, phi component. But theta, it's not moving in theta at all, so it'll only have a u component and a phi component. So let's just look at that. And that's equal to negative u plus, I'll make this big U, I think. No, little u. D r bar d u plus minus d phi plus d r bar d phi plus. Oh, I should be consistent in my notation. Okay, so I'm going to put all of this in. So in 1 and 2, n is equal to minus, I'm going to look over here, and I'm going to put df dr bar u plus minus, this is not very important, well, maybe one fact is a over r plus squared plus a squared r minus r plus over r minus d. Okay, so it's this f right here. Notice at r equals r plus, f is in fact 0. But this is not f, but it's the derivative of f. And this came about by using this expression right here. We had an expression for phi plus, a detailed expression when you put all the t bar, r bar, theta bar, phi bar, that's what you, and you take the derivative, that's what you get. Nothing miraculous here. But in let me just minus n, okay, because now here the orientation is n, here the orientation is minus n, so I'm going to write minus n, and I will get plus du plus, and then plus a over r plus squared plus a squared r minus r plus r minus r minus d phi plus. Okay, for lack of, conservation of space, what I'm going to do is, this is in region 2, and that's important. In region, primes. In region primes, u plus is minus f. Yeah? And therefore, this becomes, watch for it, so as we transition from 1 bar, 2 bar to 1 bar prime and 2 bar prime, look, these guys are continuous. In fact, they're smooth because this is a smooth function. Yeah? Now, these guys seemingly are not, but they are. Why is that? At r equals r plus, this is 0. And this is 0. and therefore this is a continuous assignment. In fact, smooth, because this actually goes to 0. So it's not so trivial. The phi components as an expression don't seem to agree, but the u plus component and phi plus component agree for different reasons. The phi components agree because it just goes to 0. The u plus components agree because f in one piece becomes minus f in the other. And that is why the flipped orientation is what makes it continuous. So what we have here is a continuous assignment of a time cone or light cone. Continuous assignment of future. So we're moving on to a different topic, but before we move on, any questions on this one? Yeah? Okay. So now our goal is to head towards describing these crossing spheres. Okay, so these horizons have been filled in. It's a solid line. We just want to take this dot off and extend the lines. So what we talked about this previously, this n is past complete because this is well, I forget what that is, but as I look at it, this is r bar equals infinity. And so n is past complete over here. It is not future complete because this is block 2. Somehow, as we finish up the maximal extension, there'll be a block 3 tacked onto here, and n is going to become future complete. But if you, and the same thing argument goes over here, and also for L. Now, what about the horizons? These vectors on the horizon stay on this horizon. So as such, you know, this patch will have to be a complete vector field. And separately with this patch, once we fill this u plus equals 0, v plus equals 0. Till then, it won't be complete. So what we're going to explicitly show is that, well, I'll pick this horizon, and I'll show this, that the vector field L is complete over here. The same thing would apply to N. Okay, so on this, I need to do some sort of a color coding perhaps. On this patch, this way perhaps. The future, we have seen this before. This is v plus, where did I put the plus? Yeah, which is r squared plus a squared dt bar plus a d phi bar. This is the vector field that's on the horizon. And on the flip side, this guy is given by v plus prime, and that is almost the same as that, but because the orientation is flipped. These are the two future pointing null vector fields. They're in fact pre-geodesic. What we will do is we'll find an integral curve of this. In fact, this is a pre-geodesic. So let me focus on this guy here. Okay, and define a curve on r bar equals r plus by alpha of s is equal to r plus squared plus a squared times some function f of s. Then the r component is constant, r plus. Theta component is some constant, theta 0. And the phi component is a times fs plus any constant you want. And I wonder if O'Neill called it beta 0 plus, but that's what I called it. I will show that for a particular choice of f, this is an integral curve to something proportional to this. Remember, this is not a geodesic, but it's a pre-geodesic. We'll pick a f so that this is in fact a geodesic, and its tangent vector field is proportional to that. Okay? So let me do the following. So there is alpha s. I think I can do this alpha. I'll just get an f dot. What remains is v plus. Yeah? We'll get to that. So what I'll do is take alpha dot. And noting that alpha dot is f plus, you can easily see that this is f dot squared v plus plus alpha dot f dot, and then I have v plus. Is that clear? Just the geodesic equation. So in the first one, I just bring the f dots outside. The second one, f dot remains. We have shown this before. I think it's r plus minus m v plus. All of this is on the horizon. Okay? And I also call this alpha 0 v plus, where alpha 0, where that's okay. I need to simplify this term, alpha dot of f dot. This is nothing. So alpha dot is nothing but f dot r plus squared plus a squared d t bar plus f dot a d phi bar, and this is acting on f dot. Well, there are many ways to see this. Let me not overcomplicate in notation. This is precisely. Is that clear? Alpha dot f dot is f double dot. Derivative along the curve. If you take the derivative along the curve of any function on the curve, it's the dot of that function. So if you take the derivative along f dot, it's f double dot. Yeah? Maybe I can put some more computational details in the notes, but it's just straightforward. So then this becomes alpha dot going over here is, I'm writing this term first, f double dot plus alpha dot f dot squared v plus, as expected. So this alpha is an integral curve of something proportional to this. But what did we want alpha to be? We want this to be the null geodesic to be complete. So we want alpha dot to be actually a geodesic. Well, that's easy. What will we do? Okay. This has easy solution. You can verify it. If you put that in here, you'll get this to be 0. So we have constructed an integral curve of something proportional to v plus, and moreover, that something is a geodesic. So now let's see what happens as s goes to 0. As s goes to 0, f goes to what? And let me write explicitly. This is just an integration constant. Okay? As s goes to 0, f goes to minus infinity. Correct? Natural log of 0. Which means the t-bar coordinate is minus infinity. So this is a curve that starts at t-bar equals minus infinity. It's not, you cannot extend it to that, but actually you can, but this, we have, this is alpha. Yeah? As s goes to 0, its t-bar equals minus infinity. I don't need to repeat the same thing again, but I have beta here. Let me call this alpha, and then alpha s is equal to r plus squared plus a squared f of s r plus theta 0 and a times f of s plus, what did I pick? Some beta 0 plus prime is an integral curve of this, something proportional to this, when f of s very similar to this, natural log of minus alpha 0 s. Oh, I guess I should put plus some constant over here. My apologies. plus some smaller constant over here. You can work it out. Oh, this is for s less than 0. Natural log is only defined to be defined on positive argument. So once again, as s approaches 0, this curve approaches over here. Yeah, and then as s goes to minus infinity, you're going to trace out So what we will do is, using the u plus v plus coordinate system, write these two vector fields and show that this can be extended to over here, and you will see as a result that this is a complete geodesic vector field. Yeah? Oh, sorry, I should have put the arrow like this, because this curve is actually going from minus infinity to 0. So I should say so it's almost like this curve goes from minus infinity to 0, 0 not included, then 0 to infinity. It's a beautiful integral curve. Okay? We'll just have to remember these equations and facts to carry out my next calculation. So remember, there's this beta, this is a constant, big C, all of this plays very minor role, and little c. So I'm going to write this in the u plus v plus coordinate system and show that it just runs smoothly. There's a reason why you can extend it here. There's a deeper, it's an example of a great result that I happened to recently see. So a little caveat. If you want, you can just stop paying attention. But this is a very interesting point. What is alpha dot s? Let's look at this curve. What's the derivative of this? Well, f dot s is 1 over alpha 0, 1 over alpha 0 s, alpha 0. Oh.
Nice.
Correct. So this is 1 over alpha 0 s r plus squared plus a squared. Oh, wait a minute. Am I thinking correctly? Sometimes these tangents Did I take the derivative correctly?
Derivative is correct. Where does the a come from in the phi component?
Oh, because of this, sorry, it's a phi. This is not the curve. The velocity is not defined. No, my apologies. The coordinate system is not defined. T bar and phi bar, right. It looks like s equal to 0 cannot be included. This alpha is not defined. That is because T bar and phi bar is not defined at this point. But we know it is extendable. In the coordinate system where it is extendable, you will find that the velocity vector has to vanish. Otherwise, it cannot be extended. So we will see this in practice. Like I said, it's a caveat. Maybe I'm not explaining, even making analogies properly. But, all right. So let me construct. I'm sorry?
Where does it have to be to 0?
At this point, if it is extendable. In the extendable coordinate system.
Why? If the lambda in flat space is extendable and the tangent is on 0 and 1?
Yes, it is. That's because the coordinate system is well defined.
But you're saying that the coordinate system where it is, well,
Yeah.
it should be 0.
If you I'd rather not waste time here. Let me think about that a little more carefully. It doesn't affect what we're doing, but as I was saying it, I got carried away, and I'm thinking to myself, well, that's not entirely true. Okay. All right. So here is the claim, perhaps. The null geodesic generator in the long R bar equals R plus horizon is complete. And its integral curve is given by u plus equals 0. Well, that's easy. In this line, u plus is 0. V plus is equal to arc tan of S. Theta equals constant. And phi plus equals constant. Look at what phi plus does. Look at this phi plus. As s goes to 0, this goes to minus infinity. So, but that's okay, because this point is not included in that chart. But here, it's a nice constant. Okay, so yeah, so u plus is a function of what? T star, and T star is just constant. So, sorry, let me look at u plus. What is u plus? Well, yeah, I mean, yeah, along this one, this curve, u plus is a 0. Okay, and then v plus, so proof. V plus is equal to, tangent of v plus is this guy. Tangent of v plus is this guy, so v plus is arc tan of that. And so that's equal to arc tan exp, I'm going to put, I'm going to use the expression from the other coordinate system. Okay, at least in the top half. Bottom half, it will work out exactly the same way. R plus squared plus A squared over alpha 0, natural log of a new constant beta times S. This is for S greater than 0. You might say, what is beta? Well, beta is defined by C, the big C, is equal to 1 over alpha 0, natural log of beta over alpha 0. Is that clear? So let me do it this way. Natural log of alpha 0 S plus a constant. Correct? That's what it was. Are we good there? This is just a direct plug-in from before. I'm going to define C to be that, so then V plus is equal to arctan exp Are we good? Because when I multiply the two, alphas cancel, and you get beta, natural log of S. Just to define, just making this look a little nicer. There's nothing else going on here. But I don't need this part anymore. If I look at kappa plus r plus squared plus a squared over alpha 0, if you recall alpha 0, what's that? That's equal to k plus r plus squared plus a squared. I'm going to write this differently. R plus minus R minus over 2. If you look at the definition of kappa plus, this is simply 1. So then I get V plus is equal to arc tan exp natural log of beta S, which is equal to arc tan beta S. Okay, so we're almost there. This is just setting beta equals 1 later on. Okay, but well, let's look at the phi component. So since this is already almost taken care of, I can look at, so yeah, What is arctan of 0? 0. So you can see this is extendable. And the interesting part, phi plus is equal to phi bar minus a. I could write about just about anything. I would convince myself, because I don't remember these functions and its details, but I shouldn't. Should be honest in what we do, and I hope I have checked it. So I'm going to substitute phi bar equals a f of s plus beta 0 plus, and t bar equals r plus squared plus a squared f of s. When I substitute those precise functions, I get and I'm evaluating this at r plus. Okay? Then I get phi plus is equal to beta 0 plus minus a of r plus minus a of r plus squared plus a squared. You have to substitute these two in. I mean, it's simple enough. These two cancel the functional dependence. One is plus, one is minus. And therefore, u plus equals 0. Is the integral curve when r bar equals r plus in 1 bar and 2 bar. You extend it from 0 to minus infinity, it'll just trace out this one. So this curve, if you make it s belong to minus infinity, infinity, it just traces out that curve. Yeah? And it's complete. S is minus infinity to infinity. So the geodesics run forever. So this is one of the major building blocks of maximal Kerr geometry. What I'll do next time is finish up, but by just drawing the other pieces. What would be the other piece? It has to consist of 3 bar and 3 bar prime. And 3 bar and 3 bar prime is connected to 2 bar and 2 bar prime. Okay, so over here, there's got to be, so there'll be a 3 over here, 3 over here, and you'll get a diamond over here, and then you get a diamond over there, and then turns out you need infinitely many of these patches, these kind of rectangles, and that'll be the maximal Kerr geometry. Any questions? Like, I know some of the computations are being skipped, but I will put that up in my notes.